Hello everyone and welcome to another minute concept video regarding kinematics and projectile motion. So for this in-depth video, we're going to be discussing again what we learned about kinematics and projectile motion and how projectile motion works. So first, let's redefine kinematics as well as projectile motion. So in the previous minute concept, we learned that projectile motion is essentially just the trajectory or the motion of an object that is launched at a certain angle. And the acceleration of an object in the motion of a projectile is actually constant, and the only acceleration it's experiencing is in the vertical direction, or in other words, gravity. So let's analyze this graph over here. Based on the graph given, we can see that there are three main parts of the trajectory or projectile motion. So first is the launch. The launch has a horizontal velocity, or rather, let's do this. There's also an initial velocity upward. So that is the start of your object's trajectory or the start of its motion. And then there's also the point where it's reaching its highest point, which is over here at number 2, which is its peak. Whenever you hear the word peak, just remember that this means that it's no longer moving. It stops moving at the height of its projectile motion. So its velocity at the very top is 0 meters per second, as symbolized by the lack of a vertical arrow here. And its horizontal velocity actually stays constant. So however fast it was moving initially on the x-axis, that will stay the same. And once it's going back down from the top, it should go down in the same amount of time as the left side, because if you look closely, this half here is perfectly symmetrical to this half here. That is, of course, without external factors like wind or wind direction, wind speed, air resistance, and so on and so forth. Again though, kinematics is concerned only regarding the motion of an object and not the forces acting on an object. So that brings us to the last part of the projectile motion, which is actually the descent or the landing. Now, what is the acceleration acting on an object in projectile motion? An object in projectile motion experiences an initial velocity going upwards. If I were a person and I threw a ball upwards like this, I would have thrown it partially going up and partially going forward. That's why I have two components here, Vy and Vx. The final direction of the ball, however, that it goes to is the resultant of those two components. Now pay attention to the graph itself. We can see from the graph that the resultant actually continues being formed along this curved parabolic shape. However, if you notice, this arrow here, aka the vertical component Vy, is actually getting shorter and shorter. And similarly to the other side, Vy flips its direction. Instead of going up it goes down, and it gets longer as it approaches the ground. So why is this the case? This is because of gravity. So gravity is actually 9.8 meters per second. However, gravity is actually not just called gravity. This is acceleration due to gravity. So acceleration due to gravity. And it's important to make this distinction because sometimes gravity, if you answer in a test, what does G stand for? It's actually wrong if you just say that it's gravity. Gravity can change, of course. So this is acceleration due to gravity. And this changes on various planets. So this is Earth's acceleration due to gravity. On the moon, it could be different. On Mars, it could be different. So that's the value for acceleration due to gravity. Now, why does this matter? Right? Why does this matter? Acceleration due to gravity matters because that's the reason why our arrows up here are getting shorter. The value of gravity, or gravity in and of itself, pulls things downward. So when something is getting pulled downward, based on the properties of vectors and the positive and negative directions, that means gravity has a negative value. So therefore, gravity gravity is a negative acceleration value. So if, for example, I had something like 22.8 meters per second as my initial velocity, every second I will be losing 9.8. So on the next one, I'll be having around 13 left. I'll have 13 meters per second left. So on and so forth until gravity completely cancels out the first half of my trajectory. And that's why we reach a 0 meters per second point here at the peak. Gravity will eventually negate the entire left half or the entire initial velocity until it reaches 0. And it will continue to act on the object, and it will cause the object to have negative velocity. So for example, let's say the object moved 1 second on this side. This arrow, instead of having okay, let's just say that these two are mirrors, exact same position, for example. Instead of this being a positive 13, we would just have a negative 13 here, negative 22.8, etc. Of course, this is just for elaboration purposes. This is not the actual value because it has to be based on the given. So let's see how we're going to solve a question like this. Before we head on to the problem solving, it's important to understand that the significance of these two halves of the trajectory of an object being symmetrical is important because these two actually give you time, the total time in flight of an object, if you only solve one half. Because let's say, for example, my object made it to the peak in 5 seconds. So if I made it here in 5 seconds, then the other side should also finish its trajectory. It should finish its trajectory on the other side in 5 seconds as well. So if you want to figure that out and see if that's true, you can try flipping a coin and try counting how many seconds it stays in the air once until it reaches its highest point and until it reaches your hand again. So obviously it might be hard to time, but you might be able to see that they're actually a lot closer together than you think. If it takes 2 seconds to complete one full toss, then it would most likely be 1 second going up and 1 second going down. So that's the significance of understanding that this parabola over here is actually completely symmetrical. And of course, it goes without saying, it's a kinematic problem, therefore we're going to be using our kinematic equations. So now let's try this practice question. A tennis ball is thrown straight up with an initial speed of 22.5 meters per second. It is caught at the same distance above the ground. How high does the ball rise? So let's try and copy this here to the other side. Oops. Okay, let's label our points here. So based on the given, we have an initial speed. So our initial speed is 22.5 meters per second. So wait, okay, let's give that a color yellow. So V0 is 22.5 meters per second. Now, which among the following arrows does this correspond to? Since it says that it was thrown straight up with an initial speed of 22.5 meters per second, we actually have to change this drawing and squish it a bit. Hold on. It would look something like this. Okay, let's just draw another parabola. It would look like this. Okay, so this should be a straight line. I'm just not very good at drawing. Okay, there. So this is the end of our first vector right here. Let's use a brighter color. Okay. Okay, so this should be 22.5 meters per second. And how high would the ball be able to rise? So we know, for example, that there's going to be two halves of this parabola, right? So on those two halves, we're going to be able to get the initial velocity here on the left, the zero velocity on the top, and the final velocity on the right. Based on the given question, we are only given values on the left side, so we're going to be using the left hand values. And we're going to be working with the entire left side of the parabola first. So now, how high does the ball rise? Let's take a look at our kinematic equations again to see how these can help us. Okay. We need an equation that has delta x, or displacement. So we're given our acceleration. We're always given acceleration. Especially in projectile motion, we have to remember that acceleration is always negative 9.8. So acceleration, negative 9.8 meters per second squared. So we're given our initial velocity, our acceleration, but we have no time. And we need to solve for delta x. How do we go about solving that if we're not given another variable as well? If you watched the in-depth video about kinematics and UAM, I mentioned that we need 3 values in order to solve for any of these values, or else we'll have two variables to work with. Well, actually, our missing value here is not missing at all. If we're going to be taking a look at the left side of this parabola, we can actually get our final velocity as 0. Because if we're able to get the peak or the final velocity at the height of the parabola, we actually can get also the distance or the displacement of the ball upon reaching the highest point of the parabola. So now, let's try using an equation that satisfies having these 3 variables and having no time. And if you think that it's equation number 4, you're correct. Okay, so now let's plug in our values. 0 squared is just 0. 22.5 squared is 506.25. And 2 times the acceleration, which is 19.6 or negative 19.6 times delta x. So now we need to isolate this side. So let's change pen, and then let's see how we're gonna do that. We're gonna move this to the other side, so we're gonna have negative 506.25, and then we're going to have negative 19.6 on the right side of the equation. So from here, obviously we just need to divide both sides by 19.6 as per algebra rules. So that will get us delta x has a value of negative 25.82 meters. However, we have a negative value here. Is that possible? The answer is no, because we forgot to do the signs. So since negative and negative make a positive, this is actually 25.82 meters. So don't forget to change the signs in order for you to get an answer that actually makes sense. Now from here, where do we go now? We can go on to the question B, or part B of the question. However, of course, since it's physics, we need to use the correct amount of significant figures. So based on the given, we're given only 3 significant figures. So we're going to round off to 26.0 meters. Or actually 25.8 rather, sorry. Okay, so now that we've gotten our displacement, we can now go for how long does the ball remain in the air. So I'm going to remove this now. We're just going to leave the value of displacement. Again, if you want to watch that and how understand again how we did it, We just used the given on the left side of the parabola. We used this side here. We used the peak as our final velocity, gravity as our acceleration, and the given initial velocity. We used equation number 4. Now we need to figure out the time, or how long the ball will stay in the air. And as you can see, I've left a hint here, and the time that it takes for the ball to rise is also equal to the amount of time it takes to fall. So we can use actually the simplest equation here, which is equation 1. So equation 1 is final velocity is equal to initial velocity plus a times t. Our final velocity, as we mentioned earlier, is just 0. So let's plug in 0 here. Our initial velocity is 22.5, and we're going to be adding it to 9.8, or negative 9.8 rather, times t. So now what do? We just do algebra once more. Gonna be moving this here. So we'll get negative 22.5 on the left is equal to negative 9.8 times time divided on both sides. We'll be getting 2.29 seconds is our time, and actually it's 2.295, so let's round off to 2.30 seconds. Okay, so now that we have 1/2 of the time, again we only got the time of 1/2 here, so let's shade that area that we got this side. That's how long it takes to get to the top from the left side. And as I mentioned earlier, the parabola or the trajectory is perfectly symmetrical. So whatever the time is on this side, it's the same on the other. So what we're just gonna do is we're just gonna multiply it by 2. So the total time should be equal to 2.3 times 2. That's 4.60 seconds. So that is our answer for the first question. So now let's try going on to the next question. Let's bring this again with us. Okay. You decide to flip a coin to determine whether to do your physics or English homework first. The coin is flipped straight up. What is the velocity of the coin at the top of its trajectory? If the coin reaches a high point of 0.25 meters above where you released it, what was its initial speed? And if you catch it at the same height as you released it, how much time did it spend in the air? Now this question sounds kinda long, but what are we going to do first? Well, obviously, we're going to need excuse me, we're going to need to break it down one by one. So again, we're just gonna draw our graph. So our parabola would again look like it's going straight up. So it's gonna look like kind of like this again. So don't forget to draw the half point or the peak, just so that you don't get confused. This also serves as a reminder that if you're going to get the time, you need both sides. Our first vector is not given. It doesn't tell us what the initial speed was. So how do we solve this question if we're not given any given? As far as we know right now, all we have are these following quantities. So we have let's use the magenta pen. Okay, so right now all we have is final velocity, or yeah, we have the final velocity as it reaches the top. So Vf of 1/2 of it is 0 meters per second. Let's just put Vf top so that we can label. We also have acceleration due to gravity, which is 9.8 meters per second squared. And we do not have delta. And we also don't have time. Now, how do we get anything from here? Okay, so if you look, the first question is just asking what is the velocity of the coin at the top of its trajectory. If you recall from the definition of projectile motion, the velocity of any object at the height of its the height of its trajectory is 0 meters per second. So we actually already answered it. The answer for letter A, the velocity of the coin at the top of its trajectory is 0 meters per second. So this is for letter A. Okay, so now if the coin reaches a high point of 0.25 meters above where you released it, what was its initial speed? Okay, so it now gives us a distance. What do we do with that? Which variable here talks about distance? Obviously, it's delta x. It's the change in position. So now we're given a new value. We have delta x, which is equal to 0.25 meters. We're given these three values, and we need to solve for initial speed. So what can we solve? What equation can we use to solve this? So from this, we can actually see that we might be able to use equation 4 since we don't have time. Right? So now let's plug in our values using equation 4. Our final velocity is 0 meters per second. Our initial velocity is unknown. We have 2 times acceleration due to gravity, which is negative 9.8. And we have no time in this equation, so our last variable is just 0.25 meters. So we can simplify this even more. We can just make it VO squared plus 9.8 times 0.5, and this would make the equation even simpler again by making these two. This is essentially 1/2, so we're just going to divide 9.8 by 2, so that will give us 4.9. So that's plus 4.9. And now what are we going to do? We're just going to flip it to the other side. We're going to switch the 4.9 to the other side so that we can leave initial velocity alone over here. So let's remove this upper portion, and we're going to move our working equation to the other side. Okay, so now we're going to have initial velocity squared is equal to negative 4.9. And oh wait, sorry, this is supposed to be negative, so this becomes a positive. Okay, so now we just have to get the square root. The square root of 4.9 is 2.21, or yeah, 2.21359436, or in other words, just since we have a max of 2 significant figures here, we'll just round it off to 2.2 meters per second. So that is our initial velocity. So we used equation 4 since we have the values of final velocity, acceleration, delta x. And we weren't given time, so that's how we know that equation 4 is what needs to be used. Okay, so now the final question is, if you catch it at the same height as you released it, in other words, it drops at the same level. So if you're here, if you're right here, then it also drops like right here, or at the same height as you, basically, they're aligned. How much time did it spend in the air? So we're just gonna do the same thing that we did earlier. We need an equation that can allow us to solve for time. Now we can just get the time of the flight by once again doing it half by half. So let's use the simplest equation once again. So we're gonna plug in our final velocity, which is 0, and this is equal to our initial velocity 2.2 plus acceleration, which is negative 9.8 times time. So once again, we're just gonna transpose negative 2.2 is equal to negative 9.8 times time. Divide both sides by negative 9.8, and we'll be getting a time of 0.2244899795. But since we only have 2 significant figures here, just do 0.2244899795. 0.22 seconds. So that's half of our time. So our total time is just this times 2. Our total time is equal to 2 times 0.22. That's 0.44 seconds. So thank you everyone for watching this in-depth concept. I hope that it was clear. I know that projectile motion might be a bit confusing, especially since there's more vectors to be taking note of, and especially since some questions they hide their givens really well. But just remember that in any projectile motion question, there's always going to be two givens immediately. Your two givens are always going to be final velocity, and it's also going to be the acceleration. It's impossible to have a projectile motion question without those two values. So try to find in the question other giveaways to see how you can figure out the, for example, initial velocity or the time or the final velocity at the end of the parabola, because that can go both ways. If we were given initial velocity here, we can actually be given final velocity on this side, and this will be our initial. So it's all about how keen you are at looking at the details of a question. So yeah, that's all for parabolic motion, and I hope you guys parabolic motion, projectile motion rather. I hope you guys learned a lot, and if you have any questions, feel free to message in the comments. I can reply to them and help you guys if there's any confusion. And that's all. I hope I'll see you guys in the next minute concept and in-depth video on dynamics, particularly the first, second, and third laws of Newton. So thank you everyone, and goodbye.